हरि करना।
Now it's time to stop and take a look back. Where are we now? So let's get into the navigational map of intuitive probability for you course. In this, so far, we have completed sets and notations. In sets and notation, we have seen sets, population, union, intersection, subsection, and then the applications of sets and notations for machine learning. That's what we have seen. And now we will be getting into the probability theory. So in probability theory, we'll be seeing event, conditional probability, and independent and dependent events, additive rule of probability with mutually exclusive events and not mutually exclusive events, then multiplicative rule of probability, then finally law of total probability, and most important one, Bayes theorem. Okay, let's get into the action now. So we'll be beginning with probability theory. So in this, we'll be looking into the various topics, and we'll understand each and every topic practically. We'll do a lot of experiments, and so with that, we'll be completing the probability theory. Once we complete the probability theory, then we will move on to the counting principles. After the counting principles, we'll see probability random variable concepts, and then random variable concept will get into the distributions. While we are dealing with a random variable concept, we will also see how these uh, probability concepts can be applied directly to the NLP, natural language processing, computer vision, and normal machine learning models. That's what we're gonna see. Anyway, let's begin with probability. I'm not going to define what is probability here. Many of you know, but I don't know what to define. So I'll begin with different probability theories. So here are some examples of situations or phenomena that can be modeled using different probability theories. So the first one is classical probability theory. Rolling a fair six-sided die and calculating the probability of rolling a specific number, or flipping a fair coin and calculating the probability of getting heads or tails. We call it as a classic probability theory. Then we have Bayesian probability theory. So this uh, the predicting outcome predicting the outcome of an election based on past voting patterns and demographic data, and updating the prediction as new polls are conducted or election results are announced. These are all called Bayesian probability theory. Okay, so Bayesian probability theory is nothing but this theory uses prior knowledge and updates it with new information to make predictions about future events. Very, very important. We're going to see Bayesian probability theory in depth. We'll be taking a lot of examples. It's very, very important. So what this theory does is, this theory uses prior knowledge, and prior knowledge is nothing but the probability of occurring those events before. It will take the historical data and how many times it has occurred. Based on that, we'll calculate the probability of those events, and then we'll use those probabilities in predicting the new events. So This theory assumes that all outcomes in no, this theory uses prior knowledge and updates it with new information to make predictions about future future events. Whereas a classical probability theory assumes that all outcomes in a sample space are equally likely and assigns probabilities based on this assumption. That's the main difference between the classical probability theory and Bayesian probability theory. And Bayesian probability theory is mainly used to predict the outcome of an election based on past voting patterns and demographic data, and updating the prediction as a new polls are conducted or election results are announced. Then we have frequency probability theory. Frequency probability theory. So this theory defines probability as the limit of the frequency of an event occurring in a large number of trials. So estimating the probability of a baseball player hitting a home run based on their historical performance or a large number of at bats. So that's the best example for the frequency probability theory. So then we have subjective probability theory. This theory is based on the idea that probability is a measure of an individual's degree of belief in an event occurring and is subjective in nature. So that's why we call this as a subjective probability theory. So a doctor assessing the probability that a patient has a certain disease based on their symptoms and medical history, and incorporating their own knowledge and experience into the calculation is the best example of subjective probability theory. And doctor and the patient relation, or predicting the probability of certain disease is by the doctor, is a subjective probability theory. That's the best example for it. So classical probability theory, we know, everybody know, those are the laws and theorems that we have been studying from ninth standard. Whereas the Bayesian probability theory, that also we have seen for predicting the weather or predicting the rainfall or some sort, based on the historical data, or probability based on the historical probability. And subjective probability is your doctor predicting how much, predicting which disease you got. Then we have stochastic probability theory. This theory is used to model random processes such as those found in physics or finance, and is based on the concept of stochastic processes. Let's take one example: simulating the movement of stock prices over time using a stochastic processes such as the Brownian motion. Such as the Brownian motion is the best example for stochastic probability theory. So then after that, what we have here is fuzzy probability theory. So in fuzzy probability theory, this theory is used to model uncertain or imprecise events, and is based on the concept of fuzzy sets. So assessing the likelihood of a car accident occurring at a certain intersection based on factors such as weather conditions, traffic volume, and road quality, which may be imprecise or uncertain. This is the best example for the fuzzy probability theory. Then quantum probability theory. So this theory is used to model probabilistic events in quantum mechanics, and is based on the concept of wave particle duality and superposition. So if you want to see the example, predicting the probability of a photon being detected in a certain location in an interference experiments. So, or based on the wave-like nature of the photon and the probabilistic nature of quantum mechanics. So, this is called quantum probability theory. So, however, we'll be mostly focusing on classical probability, then move on to the Bayesian probability theory, nothing else. But you should know what all, so where all the probability applies. Based on the application, if it is in finance and no, for stock market, it's a stochastic probability theory. But if you apply for some uncertain, imprecise events, it's a fuzzy probability theory. If you apply the same to quantum mechanics, it's called quantum probability theory. If it is based on your subjective nature, based on your if it leads to the biases of the doctor and based on his experience, it's subjected to one uh, certain entity. It's a subjective probability theory and frequency probability theory, we know. So that's the reason. So these are all different types of probability theories that we have and at this moment, and it can be developed soon with the various different domains and departments. However, we'll be focusing on classical probability theory and Bayesian probability theory. We will begin with classical probability theory. I say welcome to the classical probability theory, the world of probability.